today's class we are going to be talking about data structures for graphs. If you recall, in the last class we discussed various things about graphs, right? What various terms actually, what undirected graphs are, what directed graphs are, what is a path in a graph, what is a cycle, what are connected components, so on and on, right? We are going to start using the terminology now. So, I'm going to be discussing three different data structures for representing graphs. One would be the edge list data structure, second adjacency list data structure, and third would be an adjacency matrix data structure. We will see what these are and how they can be augmented, how they can be combined to give better performances, faster running times. Okay, so the simplest data structure is what we call an edge list data structure. So, suppose this is my graph, it is a directed graph. So, this is just a graph of various flights, right. So, these are airports, the blue vertices, and the red arcs are flight numbers from a airport to some other airport. Yeah. And suppose we want to represent this. So, one way is to have two lists, one of the vertices and one of the edges. Yeah, recall each edge is a pair of vertices. In this case, it will be an ordered pair of vertices. So, we could have two such lists. So, let us see what that corresponds to. So, that is what we will call the edge list data structure. So, it's the edge list data structure simply stores the vertices and the edges in two unsorted sequences. It is very easy to implement, and this is what it looks like. These are the lists of vertices that you had, and these were the various edges. Each edge, recall, corresponds to a certain flight between two airports. So, this is a flight, let us say NW35, it goes from airport Boston to JFK, and so it has this particular node has references or pointers to these corresponding vertices here. Yeah. So, for each edge I will keep two pointers, two references to the vertices between which that edge goes. So, this is called the edge list data structure. So, it is very easy to implement. So, there are many operations which can be done very quickly. For instance, suppose there was one operation which was given an edge, find its two endpoints. Yeah. So, that can be done very quickly. You are given the certain edge and you want to find the two endpoints of that edge, that can be done. Or there was an operation called opposite, right, given an edge and a vertex, you wanted to find out what was the other endpoint, right, and so on and on. But there is one operation which is very inefficient, and that is finding the adjacent vertices of a given vertex. So, suppose I give you a certain vertex, I give you vertex DFW, and I say which are the vertices which are adjacent to this. How will I do this? I will have to go through the list of edges, and I have to find out all such edges. So, suppose I wanted to find out vertices which are adjacent to DFW, I will have to look at this edge. This edge is not an endpoint of this. So, I go to the next one. This is not an endpoint of this. So, I go to the next one. This is an endpoint of this. So, I will look at what the other endpoint is, that is LAX. So, LAX becomes adjacent to DFW, right, and so on and on. So, this is how I will have to, what I will have to do to find out the adjacent vertices of a given vertex. Yeah. So, if I look at the various operations, I can see what times they take. So, let us see, size, is empty, replace element, swap, these are all container operations. These are when I am giving you the position. So, size, for instance, is constant time. I can keep track of the number of edges and vertices in the two lists. Is empty is again constant time. If the size is 0, then it is empty. Replace element, if I give you a particular position corresponding to an edge and I say put some other edge at that location, that just take constant time. Similarly, swap, all of these take constant time. Number of vertices, number of edges takes constant time. Vertices, what does the method vertices do? It enumerates. It is an iterator over all the vertices, right. So, that would, since I would have to run through all the vertices, that would take time proportional to the number of vertices. Similarly, these are iterators over the edges. So, they will take time proportional to the number of edges. Let us look at some more interesting thing. Suppose I say insert vertex, I want to insert a vertex, then how much time should it take? It should take constant or order n? It should take constant time because these are unsorted lists. Yeah. Similarly, insert edge, insert directed edge, all of these can be done in constant time. Let us look at remove vertex. This last operation you were not able to see it very clearly perhaps, because it's getting overlapped here, but it's remove vertex. So suppose I wanted to remove a vertex, right? How much time would it take? If I remove a vertex, I also remove the edges which are incident to that vertex, clearly, right? Because otherwise, where would their edges, where would the endpoints of the edges be referring to? So I have to essentially get to that vertex, and I also have to traverse through the list of edges. Yeah. So the list of edges is, number of edges is order m. So I have to traverse through that entire list to find out which are the vertices which are adjacent, which are the edges which are incident to this vertex, and also remove those edges, which is why this operation is going to take order m time. Here when I say remove vertex, I am assuming that you are given the particular vertex you want to remove, right? Let us say you are given the position in the list. Okay? So in this manner you can look at the various, this slide more carefully and understand the times. Okay? So this is not the only way of representing a graph, right? There could be other ways. We are now going to look at what's called the adjacency list data structure. This is your graph. Here I am taking an example of an undirected graph, but all these data structures, all the three data structures that I am going to be talking of today can be used to represent both directed and undirected graphs. Yeah. So if, so in this undirected graph, how do I represent it? I have an array of vertices, an array corresponding to vertices, let us say. So this location corresponds to vertex A, this corresponds to vertex B, this location corresponds to C, D and E. That is how it should be, right. Now what are the vertices which are adjacent to A? They are B, C and D. So I will have a linked list starting from this location, which will have elements B, C and D in it, right. This corresponded to location vertex B. So which are the vertices adjacent to B? A and E. So this link contains only A and E in it, right. This was corresponding to D. The vertices adjacent to D are A, C, E. So that is why we have A, C, E in this. These lists are also unsorted lists. Yeah. So adjacency list of a vertex. So what we are keeping track of is the adjacency list of each vertex. Okay. How much space does this data structure require? I will have an array of size n. Yeah. And what will be the length of the linked list at each location? The degree of that vertex. So the total space required in this part is the sum of the degrees, which we argued is 2 times m. So the total space required is n plus m. So it should be order n plus m, theta of n plus m.
So why are we implementing this as a linked list? जो उसके adjacent edges हैं. Why are we implementing them as a linked list? Couldn't we just simply keep them as an array or something?
We could keep them in an array. That's the next data structure. We'll see what are the pros and cons for that.
Array implementation of linked list.
What?
You can use the array implementation of linked list.
No, what he's saying is, okay, we'll come to what he's saying in the next slide, right? When I show you the adjacency matrix implementation. So what's the advantage of this? How is this better than the previous data structure?
Moving a vertex.
Adjacent vertices. Adjacent, so to find out what are the adjacent vertices of a given vertex, that can be done much more quickly here. How much time does it take now? Order degree. Order degree. If I want to list out all the adjacent vertices. If I give you two vertices and I ask you, are these two vertices adjacent? How much time would you take? Order degree still. Degree of one of the vertices, let's say. The smaller one. Yeah? Yeah, this is an array. This one is an array. This is an array of just references of pointers, nothing else. There is nothing else stored in this array. You can store more information if you want. Any information associated with the vertex you can store at this location in the array. It's just an array, right? You can. Right. It's an array typically indexed by, suppose, so you typically number your vertices 1 through 1, 2, 3, 4 and so on, right? So and then that would correspond to this location. Okay. We can combine this with the edge list data structure, right? And we'll get something more complicated like this. What is this? Ye upar wala part is just your edge list data structure that I showed you. And now with each of these vertices, I have the adjacency list associated with each of these vertices, right. I have both the in adjacency list and the out adjacency list. So, from each of these elements there are two pointers, one is pointing to a list of incoming edges and the other is pointing to a list of outgoing edges. Okay. So, we have combined this in that, the adjacency list and the edge list data structure, somehow we have combined them. Okay, good. Let us see, in what regard is this better than this? Right. So, here for instance, the operation, suppose I said operation given a particular edge, right. So, here we actually have no mechanism of storing edges really, right. We are not really storing edge information, yeah. We are storing information only with regard to vertices. Given a vertex, what are the adjacent vertices?
Right. So, any information regarding the edges can be easily obtained. So, what information regarding the edges do you want? That what is the
okay.
point of this slide?
Right. So, suppose I had the same picture as before. I have this graph. I ask you flight UA 120, which airport, from what is the starting airport, what is the ending is, right. So, we have information associated with edges and that is somehow not getting represented in this.
So we can store in the elements of the list.
Pardon?
We can store with the elements of the
Yeah, you can store, there is no harm, you can store, right. So, with this, whichever was that airport, you could do that, right. But now if you have to retrieve that information, suppose you have to answer that question, given a particular flight number, right, what are the starting and the ending airports, you will have to go through this entire data structure to be able to figure that out, right. While here you could get that information very quickly.
Sir, how is the second part, the part of the in list and out list connected to the top?
That is not connected to the top.
As good as having a double arrow for an edge list. So, this thing is as good as having a double arrow for an edge list.
Double arrow, what do you mean by double arrow?
A doubly linked, in the above portion of this slide, an arrow points from an edge to its
Vertices, and from here it is pointing from the vertex to the edges, yeah,
Yes.
exactly. Okay, so let us look at what are the time requirements for this particular data structure. Let us see. Suppose I want to find out the incident edges incident to a certain vertex. So, I can get to that vertex. So, given a particular vertex, I can find both the in edges and the out edges in time proportional to the degree, the in degree and the out degree respectively, right. So, that is the incident edges. Given two vertices, are those two vertices adjacent? How much time do I need for this? So, given one vertex, I just need to run through the. So, given a particular vertex DFW and let us say MIA, are these two adjacent? Is there a flight from DFW to MIA? What will I do? I will go in the out list of this and see. No, I will have to do more, right? I will come to this. I will come to the out list and then I have to go from here to this list here. Right? This is just numbers, right? That have, or whatever. This would be a reference to this information. These are, so it depends upon how you organize it. Okay, this could be organized as out lists of edges, or it could be organized as out adjacent vertices. If it were organized as out adjacent vertices, it would have been easy. But if like here I am organizing it as edge list, so you will have to now go to the corresponding edge and see what the other endpoint of that edge is. Huh? All of that is constant time. Okay? So, these are, so there are many ways of organizing a graph. I am just giving you a very high level idea, and then for your particular application, depending upon what operation you are doing more often, you will have to choose the appropriate organization.
How can we say that it will be minimum of degree of u and common degree of v? Because worst case will be actually maximum.
Yeah, worst case would be maximum, but suppose I also kept degree information associated with each vertex. That is not very hard to do, right? Just one integer variable which will keep track of that, then I can make this. So, it depends upon where you want to optimize. If you are doing this kind of operation very often, then it makes sense to keep degree, right, and try and reduce running time. Yeah, if you are not doing this operation, then there is no reason why you should keep track of the degrees of the vertices. Okay, so third representation is what's called the adjacency matrix representation, and this is a very simple representation. Here you just have an n cross n matrix, yeah, and there would be, it's basically just binary entries, bits 1 0. There is a 1 which is a true if there is an edge between those two vertices. Yeah, so there is an edge, there is a 1 here because there is an edge between A and B. What can you say about this matrix? What property does it have? It's symmetric. If it's an undirected graph, it would be symmetric. If it's a directed graph, it need not be symmetric. Right? If in a directed graph, you can have it that this would be 1 if there is an edge from B to A, or you can have it the other way around, depending upon what you can keep any way you like. Okay, so Mij is true. That means that there is an edge ij in the graph. Mij false means that there is no edge in the graph, and the space requirement is n squared. Right. So it's again a very simple implementation. It's also quite efficient in a certain sense, right? Or let's see.
So adding a vertex means
Adding a vertex would mean creating a new new row and a new column. Yeah. So it's order n time. Yeah, order n. Order n. Yeah. So that will be order n time. Okay. So I could have, for instance, so again, there is a possibility of, so instead of having 1s and 0s, you could keep track of the edge information here. Yeah, and so you could keep. Okay. So the adjacency matrix structures augments the edge list structure with a matrix. So you could also have the edge list together with the adjacency matrix, both of them together. Right. So in the edge list, recall that for each edge you would have information with about what are the two endpoints, right? So they could be referring to the corresponding locations here. Instead of pointers, they could just be integers now, telling which row that corresponds to. And here, instead of 1s and 0s, you could just have, for the 1s, you could also have the corresponding edge. Yeah.
in the last case, which you said you have to add a column, row and column.
Yeah.
You assume the creation of the array is order 1.
Augmenting an array, right? So again, so this is an operation which is not done very often, right? Quite often the graphs that you work with are static graphs. That is, you don't add new vertices in the graph, or you don't add remove new vertices from the graph. So if you want to have a data structure which implements that, then perhaps this is not the right data structure.
We can use an extendable array implementation.
You could do that, yeah, of course, all of those things could be done. I'm not saying it cannot be done here at all, but then this would perhaps not be the best data structure to use if this was a frequent operation you were doing, adding vertices.
Even that should take order n time only, because just n add 2n minus 1 basically rows and columns elements add करने.
But then n square
Copy.
Okay, let's look at what are the times required for the various operations here. So given two vertices, to determine if they are adjacent or not is just a constant time operation, right? But now given a particular vertex, to find out all the vertices which are adjacent to it, how much time does it take? Row or column, right, which is order n. It's not order degree now, it's order n. There is a difference. Yeah, why? Because now you'll have to take that particular row or column and look at all the entries and see which are 1s and which are 0s. So that will give you order n. So incident edges, in incident edges, out incident edges, all of them will take order n. Right? Insert vertex, remove a vertex. I have put down order n squared here because I'm assuming that you have to copy them into a new array. Right? It's not very easy to take a two-dimensional array and extend it by one row and one column. You understand why? Because the problem is that two-dimensional arrays are stored as one-dimensional arrays. You know, after all, in a particular row major or column major form, right? Now, if you want to extend it now, how does that happen, right? Because you have to then move all the information, right? So that's why extending a two-dimensional array is not an easy task. Yeah, you essentially have to copy all the information into a new array. Okay, so that's all I'll have to say about data structures for representing graphs. So there are three different things you've seen: adjacency list, adjacency matrix, and the simple edge list. And you can, depending upon what operations are critical, which are the ones that you are doing more often, combine them in a suitable manner, right? If space is not such an issue, then you can keep the adjacency matrix data structure, because it's quite simple, but it requires a lot of space. It requires n squared space. Yeah. The standard implementation, which is preferred very often, is the adjacency list. So if you can't think of anything, then just use the adjacency list data structure to implement a graph. Okay, so now I'm going to go on to graph searching algorithms. So this is something that you have done in a certain sense, which is why I'm going to be taking it up right in this class. So what is a graph search algorithm? It's basically a mechanism of visiting all the vertices of the graph in some systematic manner, right? By systematic, I mean, in some organized manner, so that you don't miss out on any vertex. So the graph could be either a directed or an undirected graphs, and we are going to be assuming an adjacency list implementation of the graph for the algorithm that we will be discussing. And graph searching algorithms are the most common algorithms that you typically perform on graphs, and it appears in a whole lot of settings. Okay, so the algorithm that I'm going to be discussing now is what's called the breadth first search algorithm, or BFS for short. What does BFS do? It will visit all the vertices of a connected component. In a graph, and it will define for us what we'll call a breadth first search tree, which will be a spanning tree on this particular connected component. We are going to be discussing breadth first search on undirected graphs only today, right? Breadth first search makes most sense in undirected graphs, and the idea is roughly the following. So you start from a vertex, right, and this starting vertex, let's say call it S, it's assigned an initial distance of a 0. So we are going to proceed in rounds. In the first round, you are going to, so think of yourself as in a maze, in some kind of a maze, right? So you have a string with you, and you're going to use this to help you search the maze. So you have tied one end of the string at one location in the maze, right? And now you unroll the string by, let's say, just 1 unit, and you see where all can you reach by unrolling the string by just 1 unit, right? Those will be what we'll call the vertices at a distance of 1 from the starting vertex. After you visited all such vertices, then you will unroll the string by 1 more unit and see which all vertices, new vertices you can visit as a consequence of that, right? And so on. You'll understand all of this when we start discussing the algorithm in more detail. So we'll do this. So we'll unroll the string by 1 more unit, find out all that we can visit now, unroll the string by 1 more unit, find all the vertices that can be visited now, and so on and on, right? And each vertex we are going to give it a label, which will be that when it was first visited, what was the length of my string then, right? If it was visited in the first round, then I'm going to give it a label of a 1. If it was visited in the second round, I'm going to give it a label of a 2, and so on and on. Yeah, and what this label will signify eventually would be the distance of the vertex from the root, from the starting vertex or the root, as I call it. Okay, all of this will be clear with some example. So suppose this was my graph, very simple graph, and S was my starting vertex. So I give it a label of a 0. Yeah, and I'm going to have a queue. So this is the only data structure I need to implement this algorithm, a queue. Recall, this is very similar to your minor question. Yeah. Okay. So you have a queue, and in which you have S. So, at any point what you are going to do is look at the front element in the queue and look at all the neighbors of that front element, right. So, the neighbors of this front element are W and R, right. So, you are going to put them into the queue now. Okay. So, and S, so I am going to remove an element from the queue, remove the front element from the queue, find its neighbors and put them into the queue, insert them into the queue. When I insert a vertex into the queue, I color it gray. After I remove a vertex from the queue, I color it black. Yeah. So, initially this is the only vertex in the queue, so it is gray. So, all the vertices which are in the queue will have a color of a gray, right. So, in some sense the gray vertices are the vertices which have been discovered till now, yeah, but I have not gone beyond them, right. Gray signifies that. Black means that I have also gone beyond those vertices, and white means undiscovered, I have not reached those vertices at all. Yeah. Okay. So, let us so this is the order in which the thing is. This is the first picture, the second, the third and the fourth. Let us understand this. I had S in the queue, I removed S, colored the vertex black, took its two neighbors and put them into the queue. I assigned them a label of one more than the label of S. So, the label of S was 0. So, I gave them both of them a label of a 1. Okay. Now, let us see what the procedure here would be. I remove the front element of the queue, which is W. I will color it black. I will look at its neighbors. How many neighbors does W have? 3 neighbors, S, T and X. Amongst these, S already is black, so I do not touch it at all. T and X are white, so I will put them into the queue and color them gray. From white I color gray, gray gets colored to black. When an element gets inserted in the queue, it gets colored gray. When it gets knocked off from the queue, it gets colored black, right, as simple as that. So, T and X get put into the queue. What label do they get? They get a label of one more than the label of W. Why one more than the label of W? Because it was because of W that T and X came into the queue. When I had knocked off W and then looked at its adjacent vertices, I found T and X, and so they get a label of one more than that. So, they get a label of 2. So, this is the queue at this point. Now, I look at vertex R, which is the front of the queue. What will I do? First color it black, look at its adjacent vertices which are white and put them into the queue. Color it black, look at its adjacent vertices which are white, this is the only vertex which is white, put that into the queue with a label equal to one more than the label of R. That is what this is, right, and this gets a gray color. So, once again you see all the vertices which are gray are sitting in the queue. At any point this is the invariant you have, right. If a vertex is gray, it is in the queue. If a vertex has not yet been visited, it is white. If a vertex has been visited and removed from the queue, it is black. Okay, everyone understand this? So, next vertex we are going to touch is T. We are going to remove T from here, going to look at its adjacent vertices. How many adjacent vertices it has? 3, yeah, but the only vertex which is white is U. So, it is only U which will get entered into the queue and nothing else, and U will get colored gray. And what will be its label? 3. U will get colored gray, its label is 3, and it gets added to the queue. Yeah. So, now I knock X out of the queue, it gets colored black. I look at its neighbors which are white, this is the only one which is white, this gets a label of a 3, it gets colored gray and it is added to the queue. So, Y is colored gray, gets a label 3, is added to the queue. So, this is what the queue looks now like. Now, I remove the front element, that is 2, look at its white neighbors, it has no white neighbor, nothing needs to be done, right. So, it gets colored black and we remove it from the queue. So, the queue is now U and Y only. So, I remove U from the queue, I color it black, look at its white neighbors, it does not have any white neighbor. So, nothing to be done. Then I look finally at y, is at the front of the queue, I look at its white neighbors, no white neighbor, nothing needs to be done. This gets removed from the queue and the queue becomes empty. So, the procedure stops when the queue becomes empty. These are the labels on the vertices. Yeah. Now, what do these labels signify? One signifies that it was discussed in the first round, 2 that it was discussed in the second, and 3 that it was discussed discovered in the third round. Right. This one is also the length of the shortest path from S. Okay, if I look at this vertex u, there are many paths from S to u. Yeah. I am interested in the path which has the least number of edges on it, the smallest number of edges on it, and the path with the smallest number of edges is this path with 3 edges on it, and so this is labeled 3. Yeah, we will see why this is getting done in this manner shortly. So, one more way of thinking of this so that you understand this completely, I started from this. In the first round, I am visiting the adjacent vertices of this. So, these are the vertices which are getting a color of, which are getting a label of a 1. Yes. So, these are also called level 1 vertices, these are the vertices which are getting a label of a 1. In the next step, so although I am going one vertex at a time, but now the vertices which are going to get a label of a 2 will be vertices which are adjacent to these, right. So, which are these vertices? These are I and C. So, these are the 2 vertices which will get a label of a 2 now. The vertices which get a label of a 3 are the ones which are adjacent to the vertices which are at 2, right, and they are basically M, J, G and D, this sort, right. This is getting a label of a 3, right, and similarly we can say the vertices which are getting a label of a 4 would be the ones which are adjacent to the vertices which are at a label 3, which are these vertices. So, these get a label 4 and these would finally get a label of a 5. Yeah. Right. So, you can think of a breadth first search as dividing your vertices or partitioning your set of vertices into sets, into levels or sets. So, there are vertices at level, there is one vertex at level 0, some vertices at level 1, some vertices at level 2, some vertices at level 3 and so on, right. So, what is the number of levels going to be? Well, the number of levels would be the maximum distance of any vertex from S. Okay. Now, okay, this is what the algorithm is. So, let us run through the algorithm and then we will we'll look at it. We'll look at the other aspects of the algorithm. So, initially every vertex is given a color of a white. It's given, so du is the label on that vertex, right. On a vertex u, du is the label. So, it's initially infinite, which means I have not put any label on it, and pi u, I will come to what pi u is. Pi u signifies the vertex, the predecessor vertex, the vertex because of which u got its label, right. What I mean by this is, so for instance, let us look at this vertex C here. This got a label of a 2. Which was the vertex because of which it got this label 2? B. So, pi of C would be B. Okay. What is the pi of K? Who can tell me? This vertex got its label from either this or this. I do not know which. It could be any. Right? We'll just pick one of them arbitrarily. Yeah. So this is how. So this is the initializing all vertices, and then how do we begin? We color the vertex S, which is our starting vertex, gray. We give it a label of a 0. Its pi of u is null because it's not. It doesn't get its label from anyone else, but from itself, and we add it to our queue. Yeah, we insert it into our queue, and this is the entire process. This green should have extended all the way here. Well, what we are doing is, while the queue is not empty, we keep repeating something. Let's say we remove the element from the head of the queue. So u is the element from the head. U is the, we are not removing it yet. So u is the element at the head of the queue. We are looking at all the adjacent vertices of u. For all v which are adjacent to u, if the color of v is white, only then do we process it. If it is already gray or black, we don't do anything with it. If the color of v is white, then what do? We add it to the queue, we color it gray, and we give it a suitable label. And what is the label we give it? D of u plus 1. Whatever was the label of u, we add 1 to that and we give that to this. And since this vertex v is getting its label from u, pi of v becomes u. We add the vertex v, this such vertex, into the queue, and once we have done it for all the vertices, we do this dequeue operation, which is we remove u from the queue. This could have been done here also. It could have been done here at the end, but it could also have been done here. That's okay. Yeah, and u is colored black to signify that it has been removed from the queue. And we keep doing this till the queue has an element in it. Does everyone understand what I am saying? Yeah?
So for initializing also, so we have to do some operation. So like breadth search or something like that.
What do you mean for initializing?
So for making the color of every node to be white.
Making the color of every node to be white, what can we do? We, what is, how do we make the, what is color? Color is something like an array, right? Right? For every vertex, so there's an array of size as,
Can't we just see if the value assigned to it is less than the value which we would assign to it?
But we can also assign it, so it's, we are just creating an array. So let's say white is 0. So just assign, put 0 to all the entries in the array. We're just giving a color to, so each of these, color, d and pi, will have to be separate arrays indexed by the vertices. Yeah, so we're just assigning that. Okay, so how much time does the breadth first search procedure take? Okay, what are we doing? Basically, all the time is being spent in this loop. Yes, all the time is being because this is just how much time do I spend here? 1 for each, so order n for each vertex. I'm spending constant amount of time. How much time do I spend in this part? Constant time. And here, all the time is getting spent in this loop. How many times is this loop executed? Order n times, right? Okay, how many times is this part of the loop executed? So this is 2 loops within one within the other, right? So for each vertex v adjacent to u, I'm doing. So we are doing it as much as the degree times, right? So if I look at these statements, they are being, what is the total time I'm spending on these statements? Order, degree for each vertex, and summed over all the degrees of the vertices, right? Which is order m, twice the number of edges. If I look at, so let's look at each statement and see what is the total time, what is the maximum time that could be spent on each statement. How many times a statement is executed? How many times is statement 10 executed? Order n, right? How many times is statement 12 executed? Order m, because 12 is executed degree many times for each of the vertices, and yeah, so order m. So 12 is executed order m times in the worst case, right? And similarly, if 12 is executed order m times, so 13, 14, 15 and 16, 13, 14, 15 and 16 could also be executed no more than order m times, right? Actually, you can say something about 16. How many times is 16 executed? Order n and not order m. Yeah, because you enqueue a vertex only once. Once you enqueue it, it becomes gray. Once it gets removed from the queue, it becomes black. You don't ever touch it again. Once it becomes black, you don't ever put it back into the queue. You only put a white vertex into the queue, right? So in fact, this statement 16 here is executed order n times. And so this is also executed order n times, and this is also executed order n times. So it's only this if statement which is really executed order m times. Yes? You understand why if this is executed order n times, this is also executed, because they are one after the other with no condition in between them. Yeah. So in any case, the total time spent on the entire thing is order m plus n. Great. Okay. So what is so let's look at a couple of properties of BFS. So BFS, what it is doing is it starts from a certain vertex, a source vertex S, and it is visiting all the vertices which can be reached from S. It will visit all such vertices which can be reached from S. What do I mean by that? All such vertices to which there is a path from S, all those vertices will get visited, which means that all those vertices which are in the connected component of S, connected component containing S, will get visited. If the graph was in more than one connected component, if the graph had more than one connected component, then if S is in a certain connected component, I will only visit those vertices. The vertices in the other connected component, I will never be able to reach them at all. Yeah. So the first thing to keep in mind is that it discovers all the vertices which are reachable from a source vertex. If a vertex V is at level I, then there is a path between S and V with I edges on it. Okay, I have not told you what a BFS tree is. So let's first understand what a BFS tree is. Good. So my slide order is a bit wrong here. What is the BFS tree that we have generated as a consequence of this? So recall that for each vertex, I have kept track of one edge which gave that vertex its label. Yeah. So let me consider the following subgraph of the graph G. What is the subgraph? The set of vertices are all the vertices which are reachable from S. Yeah, all those vertices which have a pi of V which is not null. Right? And S was given a pi of V which was null. So pi is also known as the predecessor. Okay. So each of the vertices which have a predecessor is the set of vertices V pi. So every vertex is given a predecessor. Every vertex which was visited is given a predecessor. Right? So it's basically the set of all vertices which are visited. And what are the edges? Edges in the subgraph? The edges in the subgraph are the edges from the predecessor vertex to this particular vertex for every vertex. So let me illustrate this. Let's look at this picture here. Right? What is so in this picture, if I ignore the dotted edges, if I just keep the dark edges with me, the solid edges, they are this is the subgraph that I am talking about, right? Note that each of these vertices has a predecessor except for the starting vertex. This has no predecessor. And what is the predecessor of this? It was this, the predecessor of this was this, and the predecessor of this was this. So these are the three edges that I am including in my subgraph. The predecessor of this is this, the predecessor of this is this one. This was level 2. At level 3, when I had vertices, this has the predecessor as this had a predecessor, let's say this, this has as its predecessor this, n has I as its predecessor, n could also have had m has I as its predecessor. Yeah, is this clear to everyone? Because this vertex was discovered because of I, when I took I out from my queue and looked at its adjacent vertices which were not yet visited, which are colored white, then I found m, n and j. So, m, n and j have as their predecessor vertex I, and D and G have as their predecessor vertex C. K could have G or J as its predecessor. So, let us say we decided G as its predecessor, and H has D as its predecessor, and L has G as its predecessor, right. So, these are the predecessors, and then finally P has L and O has K as its predecessor.
It's not necessary that G and J are at the same level.
G and J are at the same level, yes. Why is it not?
Necessary.
It is. They both, why are they at the same level? Because they both get the same label, same level number.
It's not necessary that they get the same level.
They would, it is necessary, right, because they are both adjacent to vertices which have label 2. G is adjacent to a vertex which
In
is,
this case, it's okay, but I'm saying for deciding for an element K which has 2 predecessors,
yeah,
we will see which predecessor has the shortest label, the smallest
no,
label.
both will have the same label then, both will have the same label. So, if there was such a, you cannot have a vertex which has 2 predecessors at different levels.
This dotted line is only because of the order in which you use the dotted line is there because order can be different, like we can.
Right. Okay. So, this is the predecessor information, and these solid lines now form a spanning tree. Why do they form a spanning tree? How many solid lines are here? How many solid lines do I have? N minus 1. Yes? Why? Why n minus 1 and not why n? There is no edge entering A, because A did not have any predecessor. Every other vertex has a predecessor. For every other edge there is one solid line, exactly one. So, exactly n minus 1 edges, right. And using these solid lines I can go from A to any other vertex. Yes, if there is a solid line entering here, that means that I can come to this vertex from that vertex, right. And there is a solid line entering here, so I can come to this vertex from, there is a predecessor of that, and there is a solid line entering here, so I can come from here to, I can come to this vertex from some other, and so on, right. So, eventually I hit the root. So, basically starting from S I can get to every other vertex. So, this is a tree, it is a connected graph, these solid lines form a connected graph with exactly n minus 1 edges. So, it has to be a tree, a spanning tree, right. Recall that we said that if a connected graph has no cycles in it, then it has n minus 1 edges. If a connected graph has n minus 1 edges, then it has no cycles in it, and it is a tree. So, this is what we have. This is called the breadth first search tree, the BFS tree. This spanning tree that we have, which is these solid lines, is the breadth first search tree. So, I think in the previous, in both the examples I had this. So, this is the breadth first search tree here, the blue lines, right, that they form the breadth first search tree here, right. Once again, for each vertex I have just darkened the line, I have not drawn the arrows here, but I have just darkened the line, because of which was corresponded to the predecessor, because of which this vertex got its label. This vertex got its label 2 because of this vertex, this got its label 2 because of this vertex, and so I have darkened these lines, and this forms your spanning tree. So, this is the breadth first search tree. Okay. Let us quickly go on. So, this is the breadth first search tree. Okay, so I will switch over to the screen to show you something. I did not. Great. So, what has really happened is that we started from this vertex S. These were my vertices at level 1, these were my vertices at level 2, and so on. let us say the largest level was 7, right. Now, this will answer some of your questions also. So, when I was at S, all these vertices which are here at level 1 are adjacent to vertices in S, that is why they are at level 1, right. The vertices in level 2 are all adjacent to vertices of level 1, that is why they got the level 2 number label 2. They got a label 2 because they were adjacent to some vertex, maybe more than one, but they were adjacent to some vertex in level 1. Could these vertices have been adjacent to S? They would have been in level 1, because when I looked at all the adjacent vertices of S, I would have discovered this vertex and put it in level 1 instead. So, such an edge cannot appear. Yeah. So, this is the nice thing about this structure that you get. I am not showing the tree edges here, I am just showing all the edges of the graph now. The edges of the graph, all the edges of the graph just go between adjacent levels. They cannot skip a level. I cannot have an edge which skips a level. It cannot go like this. This cannot happen. Why? Because when I was, this vertex would then have been in this level instead. I made a small mistake. I said all the edges go between adjacent levels. They could also go within the same level. Yes? They could also go within the same level. Yeah. Why could they? They could easily, I could easily have this. This vertex was adjacent, these two vertices were adjacent to S, but they were also adjacent to each other. No harm. Right? Even later. So, this is what the graph looks like now, and this is the important property of breadth first search that you have to keep in mind. Right? And certain edges we have called them tree edges. So, this is my BFS tree, this edge. So, my BFS tree would look like this now. So, let us say these edges, and then from each one of them I have, let us say something like this. Right? So, I am basically covering all these. So, for each of these vertices is getting its level number because of a certain vertex at the previous level, and it is this edge that I have included in my BFS tree. So, this is what my BFS tree.
Count the edges that go from elements of the same level to each other. If you have two elements of the same level which are connected,
Right.
we won't count those edges in the tree.
No, no, no. If I have an edge between two vertices of the same level, such an edge, this edge is not part of the BFS tree. Why? What are the edges which are in the BFS tree? The predecessor, right? This vertex did not get its level number because of this vertex. It got its level number because of this vertex. So, it is this edge which should be part of the BFS tree and not this. Yeah. So, let me.
The multiple edges leading to a node, we take only one.
We take only one. Okay, great. So, we have that. So, just to show you all those things that I just said to you. So, I had organized it like levels, but it is the same thing happening here, right? These are the levels now. 0th level, level 1, level 2, level 3, level 4, level 5. As you can see, all edges are going either between adjacent levels or within the same level. This vertex could have gotten its level number from either this vertex or it's this vertex. So, I picked one arbitrarily, and this I included in my BFS tree. So, the BFS tree is not necessarily unique. Yeah, but the level number of each vertex will be unique. Why would it be unique? The level number of a vertex would be the length of the shortest path from S to that vertex. Why shortest path? We have not proved yet. Right? So, if there is a path from A to a certain vertex of length 6, right, then this certain vertex, let us say whatever Z, will get a label of at most 6, right. So, if the shortest path was of length 4, then this vertex cannot get a label of more than a 4, right, because on that path. So, if there is a path of length 4, what does that mean? There is S, there is the first vertex, the second vertex, the third vertex, and then this vertex Z. So, then the first vertex would get a label, which means that the first vertex is adjacent from S. So, it will get a level number of 1, the next vertex will get a level number of 2, the third vertex will get a level number of 3, and this vertex will get a level number of 4. Yeah. So, that is why each vertex gets a level number equal to the length of its shortest path from S, and that is unique, right, no matter what order you know. So, we said in choosing the predecessor edges you could choose any one, but the level numbers would be unique for each vertex because it corresponds to the length of the shortest path from the root. Okay. So, so with that we are going to end today's discussion on breadth first search. We are going to be using breadth first search for finding the connected components in a graph, and we will see that in the next class.